For tensile tests, we performed two experiments, one on the 1018 steel and one on the 1045 steel. This graph right here is the one of 1018 steel. As you can see here, the red line represents the elastic deformation. The intersection between the black line and the blue line represents the maximal point until elastic deformation. If you release the sample at this point, it can return to its original form. And from this point on, it's plastic deformation, and you can't return to its original form. This last point represents the breaking point. As well as for the 1045 steel, here's the elastic deformation, plastic zone from this point on, and the elastic zone and the breaking point. Here are the results for the impact test. I performed two tests on two different samples, two in 1018 steel and two on 1045 steel. And each one of the samples I performed one in 22.4 degrees Celsius and the other one at minus 15.2 degrees Celsius to see the changes in temperature. Now for the length and width and thickness, it's all the same because it's Sharpie test done to the same measure. Now going to the energy absorbed, you can see that samples that were at room temperature absorbed more energy than the ones who were at minus 15 degrees Celsius. And you can see that also the ones that were at room temperature had ductile fracture, and the ones at minus 15.2 degrees were brittle fracture. And you can see that the 1018 steel absorbs less energy than the 1045 steel. Now as for steel 1045, these are the results. I performed two tests on this sample to get a better result and more accurate one. I got a 285 measure diameter average and a 460.5 result practical hardness average. Then I did some analysis on a theoretical way and I got 193.542, and the investigated hardness was going from 170 to 210. Now as for the steel 1018, I also performed two tests and I got an average of the measure diameter 3.05 and an average of result practical hardness of 395. Now the theoretical hardness I got 193.928 and the investigated hardness was 127. Now as for the Rockwell hardness results, the steel 1018, I got an average of hardness of 51.75 and the investigated hardness is of 15. Now for steel 1045, I got an average of hardness of 53.75 and investigated hardness of 4. Now for the Vickers test, I had to perform the test twice and I had to measure two different diagonals. For the first one, I got a 44.25 average measure of the measurement 1, and for the measurement 2, I got a 43.1. For the first one, I got a 281 hardness Vickers, and for the second one, I had 295 hardness Vickers. The average practical hardness was 288. The result of theoretical hardness was 291.585, and the result of the hardness investigated was 170. For the steel 1018, I performed two tests as well. For the first measurement, I got 55.5 average, and for the second one, 54.75 average. For the first measurement, I got a 180 hardness Vickers, and for the second one, I got a 187 hardness Vickers. The average practical hardness was of 183.035, and the theoretical hardness was 183.5. and the investigated hardness was 131. For the metallographic test, I obtained a result of 1,150 grain size for steel 1045 and a result of 1,425 for steel 2018 at 500 times magnification. This last practice for me was really interesting and really good because in this practice we applied all the test to just 2 samples, and we were able to have a more complete analysis than we had before on the previous practices. I think it's very important for us as engineers to know all the properties of a material if we're going to use it for a certain purpose, to know if it's going to fail or if it's going to withstand any effort or any force or load that it's going to take during for its application.